So remember, you're just going through this list. And you're marking down what you think is true, and what you think is false. Just a guess at this point. Just a guess. I don't know if this will work or not. We're going to try. Probably help. In. All right, hopefully that will put the mic on me. All right, I'm trying to record these two so that if you miss a day, you got something to work on. All right, so we've got 6 people. All right, just give me a thumbs up for true, and a thumbs down for false. All right, and what I'm going to do is I'm just going to create like a little tally sheet so we can see what we agree on. Number 1 says the Earth stops spinning, would all float in outer space. Thumbs up for true, down for false. Give me a little thumbs up or thumbs down so I can take the recording. Put it down. Yeah. Okay. 1 and 5. Number 2, there is no gravity on the moon. Thumbs up for yes, thumbs down for no. True, false. Then I have one or the other. Okay. 1, the other one. Okay. NASA has an anti-gravity room where the gravity can be turned off and people can just float around. Number 4, it is possible to shield the force of gravity by using lead or other materials. So I can block out gravity by using lead or other materials. Sir Isaac Newton discovered gravity. Sir Isaac Newton discovered gravity. Number 6, you have no mass in space. In space, you are massless. Number 8, weight is measured in kilograms. Science is going to measure weight in kilograms. Number 9, there is no gravity in space because space is a vacuum. No gravity in space because space is a vacuum. Okay. Number 10, we were able to remove all the air, suck all the air out of this room, and begin to float around. All right. Now, these are pesky little things in science that we like to call misconceptions. Okay? Misconceptions are just ideas that sound good, sound right, but are actually not quite true. Okay? Now, this is not meant to trick anyone, but this is just to get us thinking about what we know and we don't know about gravity. All of these, get there? All of these are false. Okay? If the Earth stopped spinning, there'd be some serious problems. Some serious problems, but us floating away is not one of them. Okay? There would be a perpetual night side of the Earth, there would be a perpetual day side of the Earth, or a day would last 365 days, or a year, or yeah, a single cycle. Anyway, lots of problems. Gravity is not one of them. There is less gravity on the moon. So when you see the moon bounces, they're just kind of like hopping along, right? But that pull down, there is some gravity there, right? Some gravity. NASA does a lot of training for no gravity situations, but they don't have a room. They have a couple things. They do a lot of training in water. So they'll put like weights on to make your buoyancy equal to the water so that you appear weightless. They also have a plane, which is really cool. They take the plane up real high in the air, then they go into a nosedive. And basically what happens is the people in the plane are falling at the same speed the plane is, so you look weightless. I know I'm showing my age a little bit here, but if anyone's ever seen Apollo 13, that's how they filmed a lot of those space scenes in Apollo 13. They took Tom Hanks and all of them up in a big plane, and they dropped the plane, and then they would level out and go back up and keep dropping and doing that all day long so that they could get that weightlessness look. This comes from like Superman, I don't know, you can't see through life for some reason, don't have to why, but that has nothing to do with science. Sir Isaac Newton coined the term gravity, but you can't discover something that's been here since the beginning of time, so you can't discover that. He's very important for gravity, but you can't discover it. You always have mass. Mass is just the amount of material that makes up your body. So whether you're in space or you're here on Earth, that doesn't change. What will change is your weight. We'll talk about that later today. There's no gravity in space because you're far from the Earth. Like again, there's less gravity. But if there was no gravity in space, we wouldn't go around the sun. The sun's gravity holds the Earth in place. That's what causes us to go around the sun. There's 100% gravity in space. This has usually less than the experience here on Earth. Mass is measured in kilograms. Weight is in pounds, right? There's no gravity in space because space is a vacuum. It is a vacuum, but there's always gravity. And if we could suck all the air in a room, we would explode, do a big bloody mess because gases would expand in our bodies and everything like that. But we would not float. Right? We would not float. Any questions about these? So now that we know that we don't know everything about gravity, let's learn a little bit about gravity. What do you guys say? So first off, let's answer simple questions like, what is gravity? Well, gravity is a weak force. Yeah, sorry guys, we're back on the slide. Gravity is a weak force that exists between all objects. That means right now in this room, you have gravity. I have gravity. We experience each other's gravity. We don't notice it because there's a bigger object that has a bigger gravity, which is what? Earth. Yep. Earth has a much stronger force of gravity than you or I. But if we were teleported out into deep and outer space, away from far, far away from all objects, we would start to notice each other's gravity. The pen or pencil that you're writing with has its own gravity. We don't notice it. It's too small. But if we were in outer space, deep away from everything else, we would start to notice that this has gravity. Okay? So, what gives an object's gravity, or what affects an object's gravity? First off, gravity is a weak force. Guys, this is a Goldilocks thing. Anyone know the story of Goldilocks? Not too hot, not too cold, just right, not too big, not too small, just right. Gravity is perfect. If gravity is just a tiny bit stronger, everything gets sucked into a black hole. If gravity is just a little bit weaker, you never come into existence. Nothing ever comes together. So gravity has this perfect balance of allowing us to clump things together, pull objects together, but not so strong that it crushes them, that it brings everything into one space. So gravity is a really interesting force. And as we talked about, the force of gravity is not always the same. It depends on two main factors. The first factor is size. The size of the force of gravity depends on the mass. The bigger the mass, the bigger the gravity. So who has the most gravity in this class? Roman soul. Who has the most gravity in this class? Me, because I have a little bit more mass. We'll say a little. Okay, just hang on top of it. We'll say that there's a little bit more mass in me than it is in you. Right? So therefore, out of all of us, I have the strongest force of gravity. Okay? The gravity between these two elephants is a lot stronger than the gravity between these two mice because of the mass. The more mass, stronger the force of gravity. The less mass, the weaker the force of gravity. That's simple. So those elephants are going to be experiencing a much stronger pull than those two mice. The second object, or second factor, that determines how much gravity there is the distance between two objects. Right? Let me give you an example of that. Remember, I said the bigger the mass, the bigger the gravity. Which is bigger, the sun or the earth? The sun is much bigger, okay? 100 times the size of Earth. Much more mass. So which has a stronger force of gravity? The sun. So why are we stuck here on Earth? Why are we not pulled into the sun by the stronger force of gravity? Well, it has to do with this second factor. Distance. Are we closer to the Earth or are we closer to the sun? Closer to the Earth, right? We're in contact with the Earth right now. So we're going to experience the Earth's gravity more because we're closer to it. So these two ants, all these ants have the same mass, right? So that's not a factor here. These guys are going to experience stronger gravity because they're closer together. These ones are going to experience less gravity because they're further apart, right? Even though the sun has a stronger force of gravity, it's actually really far away. Relatively. Right? We're much closer to the Earth. Now there is an object that affects the Earth due to its gravity. Does anyone know what that object is? What's the next closest object to the Earth? Moon, right? The moon's gravity does affect the Earth. Does anyone know what it creates in the water? Tides. Tides occur because the moon's gravity is physically pulling the water towards the moon. Okay? And pulling that water towards the moon creates it to bulge a little bit, be a little bit higher than normal. That's the high tide. Okay? So directly beneath the moon, there is a pull away from the Earth because it is closer than the sun. Okay? So we do experience the moon's gravity because it's the closest object to us. Now, like I said, we only really notice the objects of really big objects. So you're not going to notice any of your gravity because we're much closer to a much larger object called the moon, or excuse me, called the Earth. Holy cow, good stuff. All right, the Earth is very large and very close to us, so we notice its gravity. The force of gravity on something is called its weight. So this is where weight comes in. Weight is really a measurement of force of gravity times or mass. Okay? Which means that my weight is going to change depending on where I am. I won't tell you how much I weigh because I might get caught up in my feelings a little bit, but let's say I weigh X amount. Okay? Here on Earth, I weigh X amount. If I go to the moon and I step on the scale, I feel real good about myself. Why? There's less of a pull, so guess what? That number is going to be much smaller. It's going to make me feel real good about myself. The amount of pounds that I will weigh on the moon is less because there's less gravity there. Now, if I go somewhere, let's pretend like you set foot on it. Let's say we went to like Jupiter. How are my feelings going to be? Bad. Why? Because it's going to be a lot heavier. Okay. I'm talking like Mack truck heavy. It's going to be a lot because the force of gravity is much, much stronger. Okay? So your weight is going to change depending on where you are. But the cool thing is your mass never changes. So deep, far in space, away from any planets, my weight becomes almost zero. Why? If I'm in deep outer space, why is my weight drop to nearly zero? What's not acting on me if I'm in deep outer space? If I'm not close to any planets or moons or anything, there's less of a force of what? What are we talking about today? Gravity. There we go. So because there's less gravity, I'm not by any objects, yeah, my weight's going to be zero because there's no force acting upon me. Okay. So mass is a measurement we use in science because mass never changes. Mass is a measurement of the amount of material an object is made of. We measure it in grams. Now, I say kilograms, we measure our weight in kilograms with bigger objects, right? But gram is the base unit of weight. Kilograms is just 1,000 grams, it's a bigger number. And I think a kilogram is what, like 2.5 or 2.2 pounds or something like that? Don't remember quite correctly. Some of my entrepreneurs might be able to tell me better. Okay. Everyone got what they need from this one? So, like I said, I'm not going to tell you my weight, but I'll tell you in kilograms. You don't have quite kilograms, but I weigh 143 kilograms. So that means here on Earth, my mass is 143 kilograms. Guess what? On the moon, my mass doesn't change. I'm still the same amount of blood, sweat, and tears. Okay? Still have a mass of 143 kilograms. But what do we say would change? What does change on the moon? Not my mass, but my weight. Good. Even in deep outer space, I'm still 143 kilograms because the amount of cells and stuff that make up me doesn't change. The only thing that does change is how much gravity is acting on my body. So again, mass is how much material. Weight is really the mass times the force of gravity. Mass times the force of gravity on an object. We measure it in newtons. So this is a formula. Go ahead and rewrite this out on the side of your paper so you have that formula if you need it. So we have weight equals mass times gravity. And that formula right here. Mass times the force of gravity. That's your weight. Okay. I also want you to add on here, I don't know if it's the PowerPoint or not, but Earth's gravity does anyone know what it is? Anybody? Grab the files here. 9.8 newtons per second squared. That is the force of acceleration due to gravity. So right now, that means the Earth is going down in your body at a rate of 9.8 newtons per second. That's the acceleration, and gravity will pull you down. So if I have my pen, I drop this pen, it's going to accelerate from 0 to eventually reaching what's called terminal velocity, as fast as it can go. But it's going to accelerate at that rate. So the force of gravity on 1 kilogram is called the gravitational field strength. We measure that in newtons. Newton's obviously giving a nod to Sir Isaac Newton, right? Depending on how you interpret the story, he was sitting somewhere in an orchard, and the apple falls either on him or in front of him. That leads him to ask the question of why did the apple fall? And that eventually leads him to coin the term gravity. So far, so good. So to calculate the weight of an object, you simply multiply its mass times the gravitational field strength, aka mass times gravity. This is just what we put here. Okay. So if you want to be real mean, you could do the math, figure out how much I weigh. Please don't, thank you. Almost done with these notes. The gravitational field strength of Earth is 9.8. Okay. So if your weight, let's say, you had a mass of just 45 kilograms, what is that? Well, weight equals mass times gravity. So we're going to take 45 times 9.8. So it means it's about 441 newtons of force. Newtons is, again, a measurement of force. So that means that your weight is pushing down on the ground with 441 newtons of force. Okay, that's causing your weight. You're pushing down on the ground. Any questions on that? Okay. Now, because of our time and we're a little bit behind, normally we would jump into a little lab to see what our jump is here on Earth when we go around the solar system and jump on other objects. We'll do that later. What I would like to do now, though, is just kind of continue with notes so we start talking about the Big Bang so we can get a little bit more caught up where we're supposed to be. Okay? Now, why am I talking about the Big Bang after gravity? Well, because the Big Bang occurred a very long time ago, and gravity played a super important role. So let me pull that up real quick. And if you guys would, just flip over one page and you should see start it from the top, at the very top of that page. And if my brain would function, I'd be able to pull this up a little bit faster. So guys, if we're going to start this story of Earth and all that jazz, we really have to start. Sounds and stuff because I thought I was cool at one point. But oh, this is not. Okay. Oh, teaching things for too many years. Too many copies of the same thing. This is not what I need. There we go. Here we go. Sorry about that. Okay. Hey, start from the top. Look at that. So we're going to start the story, like I said, we're going to start from the beginning. And as far as we know, the creation of the universe, as far back as we can see, comes from an event we point the Big Bang. Okay? The Big Bang occurred approximately 13.8 billion years ago. Now, billion is a number that our minds cannot comprehend. Yes, you can see a number and recognize that it has 9 zeros and that is a billion. But to actually think of and understand what a billion means is actually beyond our processing capability. To truly understand a billion, okay? Very, very hard. But 38 billion years ago, a long time ago, all right? We've been around for a long, long time. So the entire universe at that time was compressed into a single point. What came before that, we don't know. Because we can only go off of what evidence that we have, right? So the entire universe was compressed to the size. Please underline this word. Sorry, I'm masking to make that point. But the size of an atom. If you tell me, because this is going to be an essay question on your first quiz, if you tell me the universe started off as the size of an atom, or it started off as an atom, we're going to fight. Okay? It started off the size of an atom. Okay? Again, we talk about really big things in science, we talk about really small things in science. Atoms are really hard to think about. If you took this room and you filled it floor to ceiling with grains of rice, okay, full pieces of rice, floor to ceiling, and then you focus on one of those pieces of rice, you zoom in, so that single piece of rice out of the whole room of rice is the size of the room. fill that with rice, spaces in between the rice about the size of an atom. Okay? The speck of a speck of a speck is really the way to put it. Okay? Very, very small. The entire universe was incredibly small. Now, that point, all right, it was unstable. Right? It didn't stay together very long. And so, boom, right? There's no boom, no space for sound to travel, but the bang happens. And what do I mean by the bang happens? Is that there is a super, super rapid expansion. Right? It happens so quickly that we actually have to slow down time to talk about the different stages. What is the smallest unit of time that you guys can think of? Like, let's start with hours. What's smaller than hours? Minutes, good. What's smaller than minutes? Seconds, good. What's smaller than seconds? Milliseconds, good. What's smaller than milliseconds? Ah, okay. So we can go further. We could like microseconds, things like that. But you can get even smaller to the smallest measurable amount of time, and that is something we call a Planck time. Okay. This is a Planck time. Point 0.0000000. You get the idea. It's a really small amount of time. Okay, it's an instant of an instant, basically. Okay, this is seconds. This is milliseconds. I mean, like we're talking minute differences in time. Okay, and what happens is it starts to expand. It goes from the size of an atom to about the size of a grape. Right, basically in an instant. That doesn't sound like a big expansion, but that is an enormous expansion in an instant, okay? So like I said, it's 10 to the negative 43 seconds. That's 1 Planck time. It basically goes from the size of an atom to the size of a grapefruit. Now, what's that baby universe like? Again, we are still 0.0000001 seconds in the existence of the universe. There's no solid matter. Okay. At this point, the universe is a hot, hot, hot ball of material. Not even atoms exist here. Okay. There's no solid matter. It's energy and temperature and space. All right. Water boils at 100 degrees Celsius. Okay. So it's a little hot there. A little hot in this early universe. And it was so hot that basically matter, as soon as it was created, it was destroyed. Right? And that also releases more energy. There was a battle between two things: matter and antimatter. Matter and antimatter, the best thing I can give you is like this: 1 and -1. 1 is matter, -1 is antimatter. They are opposites of one another, and they're attracted to one another. When they run into one another, what do you think happens? What do you get when you combine 1 and -1? 0. You get nothing. Okay. So what was happening is, as the matter and the antimatter were colliding, they would release a huge amount of energy. They would take themselves out of existence. For reasons we do not know. For reasons we do not know. There was slightly more matter than there was antimatter. For example, if there were 1 billion pieces of antimatter, there was 1,000,001 pieces of matter. This is about the ratio. Okay? I'm talking the slightest amount more matter than antimatter. So luckily for us, everything in the universe that we see today comes from this little leftover 1. Okay? 1 in a billion. So basically, this is a soup of the building blocks of atoms. You have electrons up and up. They have little negative things, and quarks. Quarks are even smaller than electrons. Last time you'll hear me talk about this, last time you'll hear that word unless you go into like a college level physics class. Okay, quarks are smaller than electrons, which are really, really small. Basically, the super tiny parts of the atom. And like I said, battle between antimatter and matter. Luckily for us, there was slightly more matter. And that's how the universe came into existence. All right. As the universe grew, it got bigger. And as it got bigger, there was more space. And if there's more space, there's more room for the heat to spread out. And so what happened is two things are going to hold true. The universe is going to get bigger, and it's going to get colder. Right? So the universe continues to expand and starts to cool at 0.00001 seconds after the Big Bang. So we're still not even to 1 second yet. Okay, this is all happening in Planck times, instant of an instant. Okay? After that amount of time, the Big Bang was cool enough for protons and neutrons, the core of the atom, to start to form. Okay? Now, protons and neutrons are much bigger than electrons. So now we're starting to get matter. Now we're starting to get things to clump together a little bit. So in the core of the nucleus, we're not going to talk too much about this. There's little positively charged things called protons, and then little neutral things called neutrons. That makes it the core of an atom. And flying around the outside, you have these little specks called electrons. And they hold a negative charge. Okay? Basic structure of the atom. So now we have the building blocks to atoms. We have protons, neutrons, and electrons finally on the board. But it's still too hot for them to come together. Okay? It's like a super dense soup of building blocks. And it's so dense that there's actually no light. Okay? Light is a form of energy. What these light bulbs are doing is they're converting electricity into light. Okay? Light has to travel through space. It's traveling from the light bulb down onto the floor, down onto the table, and reflecting in all different directions. But in this early universe, as soon as light would go to be created, it would run into something. So this is still before light. Light does not exist yet. The universe is dark. It's a dark mass of building blocks of atoms. Then we enter what we call the dark age. Now we're at 3 seconds. 3 seconds after the Big Bang. That's it. So 3 seconds after the Big Bang is where we're at right now. And for the next 300,000 years, there is still two things happening. It gets bigger and it gets colder. And there's still no light. It's still dark. The universe goes from about 100 million degrees Celsius down to a nice cool temperature of 10,000 degrees Celsius. Remember, water boils at 100. Still quite hot compared to our standards, but compared to where it was, it's cooled down a lot, right? Because it's finally so cool, now we can have the parts of atoms clumping together, okay? So protons and neutrons form nucleuses, the electrons orbit around outside of the nucleus, and we get the first atoms after 300,000 years. Okay? Now, that early universe was 3/4, 75% hydrogen, 25% helium. We're not going to talk much about this table, or too much about this table. We're going to talk some about it today and more later. But here's hydrogen, smallest of atoms. Got 1 proton, 1 electron, and no neutrons. Okay? This is the most basic of basic simple atoms that we have. It's also the most abundant because 75% of the universe from the start was hydrogen. We come over here, we have the second largest atom, which is helium. Helium has 2 protons, 2 electrons, and actually 2 neutrons. Okay? These are the only 2 atoms that exist. What do we need to breathe? We breathe out of the air. Oxygen, guess what? There's oxygen, doesn't exist yet. What kind of life forms are we? What's our main atom in our body? Anyone know? Carbon-based life forms. Doesn't exist yet. The air that we breathe is about 70% nitrogen. Doesn't exist yet. Okay, so we don't have any of the things we need for life yet. We just have hydrogen and helium. Just basically empty space of gas. Finally, after 300,000 years, what starts to happen is these atoms clump together. A bunch of helium builds up. Now, as they clump together, they add mass. What do we know happens as you get more mass? Say again. More mass equals more weight. That's true. But what else does a bigger mass mean? What do we talk about at the start of class today? More mass, more pull of gravity. So that's important. Because what starts to happen is the atoms start to clump together, which collects their masses together, which makes their force of gravity a little bit stronger. So they have a longer pull. So now they're pulling more atoms in, which adds to their mass, which makes them bigger, which makes them stronger. Start pulling in more atoms and more atoms and more atoms until gravity and pressure become so strong it starts crushing atoms together. And then, like a light switch, we get the first light traveling across the universe. What I just described was the formation of a star. Okay? The star is nothing but hydrogen. It builds up, gets strong enough, it begins a process called nuclear fusion, which we're going to talk a lot about, where it crushes atoms together with light. So 300,000 years after the Big Bang, we start to get the first starlight traveling across the universe. Okay? So out of darkness, these stars start to ignite. Now, I know it seems silly to talk about like Planck times, the first 3 seconds, and then like the first 300,000 years. We're going to skip over the next, I should say 15, I should say 13. Please change that if it's wrong in your notes. For the next 13 billion years, we're going to just kind of clump it together. The temperature goes from about 10,000 degrees Celsius down to the current temperature of space, which is negative 270 degrees Celsius. It got a bit frosty out there, guys. Okay? A little cold. Water freezes at 0. So, we complain when it's like 30-some degrees outside. That's where water freezes. It's negative 207. It's cold. Okay? Bring a jacket if you're going to outer space. Through this time, 2 things keep happening. Bigger and cooler. Bigger and cooler. Bigger and cooler. Also during this time, clouds of gas and dust continue to condense because of gravity, form stars. Those stars go through a life cycle, which we'll talk about later, hopefully this week, maybe next week. They die, they explode, they create material for new stars, and so on and so forth. Okay? Eventually, this leads to the formation of planets and solar systems. And eventually, about 10 or 9.5 billion years after the Big Bang, our neighborhood starts to form. Okay, our solar system comes about, and the planet Earth is created. Okay. Does this have? It's not. Okay. All right, I'm going to try and get through a little bit. I know today's a lot of talking. I really do apologize, but it's just because we're trying to get caught up on stuff so that we're not so far behind. But I would like to talk a little bit about that next page about what evidence do we have, because it's great for me to sit up here and tell you guys that the Big Bang occurred, but I have to back it up with evidence, okay? And we do actually have evidence to support the Big Bang. And let's talk about what evidence we have. Maybe. Here we go. Now, this is normally a do now, but let's just talk about this. Do the thing. Oh, that's not how we do this. Okay. Now, normally, like I said, normally this would be a do now, but let's just talk about this. Here we have a picture. Turn on the light so we can see a little bit better. Here we have a picture. What happened here? What is that? Forest fire. Great. How do you know? Were you there for the forest fire? Well, that's my first question. Were you there for the forest fire? No. So you didn't see it happen. Am I correct? So, how do you know a forest fire occurred? Now, how do we get it? Bird trees. Hey, there's one. Cool. So I can see that over here we have some green trees that weren't affected. Here we have some yellow trees, and here we have some charred up trees. So we can tell if a forest fire happened. Good. What else can we tell? Okay, it stopped because we still see some green. Which direction did it come from? Did it come from, let's say, from the right or from the left? Where did the fire come from? The right side, right? How do you know? This side's all burned, this side's still not all the way burned, right? But wait a minute, guys, you didn't see a fire. I don't see any smoke. I don't see any fire. And yet, without being there, without having some big piece of evidence of fire, we can still work backwards to figure out what happened. Was anyone here 13.8 billion years ago to see the Big Bang? No. No one was there. So some people say, well, no one was there to see it. Did it really happen? Did this forest fire happen? Yeah, because we see the evidence. Okay? And what we're going to do is we're going to work the same way through some of the evidence with the Big Bang. Okay? It's enough. It's one thing for me to say it. It's another thing for me to show you how do we know. So what we're going to do is we're going to look for some evidence. What we're looking for here, guys, is the smoking gun. Okay? What evidence do we have that the Big Bang actually occurred? Does anyone still see the papers enough to write, or do I need to put the lights on? Are we good? So, if the Big Bang was such a massive explosion, okay, such a massive expansion, so much energy, so much heat, there has to be some leftover evidence, right? There's got to be something left over for us to find. So, imagine this is how time normally works, right? Moving forward. This is the Big Bang. It starts off with that little grapefruit, black watermelon in this picture, right? And then boom, that rapid expansion and all that. What we want to do is we want to take where the pieces are right now. We want to rewind that time. More Big Bang. Okay? To see if we can put the pieces back together, figure out what it looked like from where we're at today. So here's the question. What might we look for? What do you guys think might be out there? What kinds of evidence might we look for supermassive, rapid expanding, hot universe? What do we see from this explosion? Possibly, if we were focused more on Earth, for the Big Bang, we're focused on the whole universe. So let's think a little bit bigger, huh? Okay, can I change? Yeah, heat. Let's go with it. Heat and energy. Okay, so somewhere out there, there should be heat. Heat or energy, right? We might also look for light, right? How long after the Big Bang before light occurred? 300,000 years. So we could also look for that early life, okay? So we would want to look for light or energy. The Big Bang did happen. We should be able to find some energy still traveling through space, right? That shock wave, that leftover energy. And what do we say the universe was constantly doing? Constantly expanding. Constantly expanding. So do you think it stopped? We don't know. But what we should do, we should try and figure out if we're still moving, right? That's an important feature. If we're still expanding, that's good evidence that we were at one point close together. So if the universe is expanding, things should still be getting farther away from everything else. And guys, that's part of the key. Expansion is not me getting further away from one person, but getting closer to another. That's not expansion. Expansion would mean that we are all getting further away from each other all at the same time. Sometimes scientists like to call this the raisin bread model. If I'm breaking raisin bread, start off with dough and raisins, right? And all those raisins in the dough are very close together. And then I put that dough in the oven. And what happens? Well, that bread starts to rise and starts to expand. So every single raisin in that bread is actually getting further away from every other raisin in that bread because it's expanding, okay? So if that's true for raisin bread, it should also be true for our universe. If the Big Bang happened and expanded all this time, we should still see evidence of that expansion. Okay, so those are the two main things that we're going to be looking for. So, what is light? This is a hard thing to think about. Light's something we deal with every day. You may not know what light is. This is light. Light is a wave of energy. Okay? And just like ripples on a still pond, it travels outward at a predictable speed. Okay? Light is made of little things called photons, where the word photograph comes from. One piece of light is called a photon. And they travel through space in predictable ways. Light doesn't get to decide where it goes. You set it off on its path and it travels that direction until it hits something. The sun is giving off light that travels all the way through outer space and smacks us in the forehead when we're standing outside. Okay? If it doesn't hit our forehead, if it doesn't hit the Earth, it continues to travel outward to the other planets and then out of our solar system. Okay? The speed of light is something around 299 million meters per second. That translates to roughly 186,000 miles per hour. Light's pretty quick. Okay? If I turn on the lights in this room, it's instantly bright. But if we slow down time, we would see this would slowly start to glow. The light would slowly start to come down and outward in all directions if we were able to slow down time. But because it only has to travel like 10 feet to the ground, and it's traveling at 200, we're just going to call that 300 million meters per second, all right, it appears instantaneously to us, to our eyes. Okay? Why is that important? Well, if I said, your friend left you, or you missed the bus, or something, I don't know, and the car or the bus was traveling 50 miles an hour for 2 hours, how far away is your friend? So 50 miles an hour for 2 hours. How many miles away is your friend? 100 miles. If I know how fast you're going, and I know how long you've been traveling, I can tell you're roughly 100 miles away from me. Let's take that on a bigger scale. If we said light travels at nearly 300 million meters per second, and it's been traveling for 13.8 billion years, we should be able to tell where that first light is in outer space. It's going to be a little bit bigger of a number than our 100 miles away, but we should be able to do that. We should be able to find that leftover energy, that leftover light, still traveling out there today. Okay? Now, how am I doing on time? All right, got 20 minutes left. We won't use the whole 20 minutes, but. All right, so guess what? This is a funnier story in science. Not every discovery happens on purpose. Once we realized what we were looking for, there was a super, super big race to find that light, find that leftover energy. And whoever found it was probably going to win the Nobel Prize and become nice and famous. Now, what happened is, how do we search outer space? What's one of the tools that we use to search outer space? So if I wanted to look up at the moon right now, what would I use? Telescope, exactly. Okay, there's different kinds of telescopes. What I would use to see the moon is a light telescope. It uses light, magnifies it, makes that image. There are other forms of energy, like radio waves, and things like radio telescopes. Okay, they don't necessarily detect incoming light, but other energy on the bigger end of the spectrum. But the important thing is they can be real big, and they can reach out real far and deep in outer space. So what these scientists did was they built one of these radio telescopes. And this was back, I think, like 60s, 70s. So not a lot of technology, right? You're not going to have your iPhones or anything like that. But technology is starting to come about, and we're starting to get these big, big telescopes called radio telescopes. You guys ever seen like an old Western or like cartoon where there's an old person and they can't hear? They put up like one of those like amplifiers to their ears. That's basically what a radio telescope is. It's a big box that basically takes in all of the incoming radio waves and just kind of funnels it into a spot that can be read. Okay? This big open space is open to the outside. So these scientists built this telescope and they turned it on. They were real excited to like hear this pristine, radio wave press down, and all they heard was this hum. Constant hum. And so they're like, man, we must have made a mistake, so let's figure it out. They looked through their plans, they redid stuff. One of the theories they came up with is that there were these pigeons that were living in their telescope because it's a big open space, and where pigeons like to live. And where pigeons live, they shit. And so literally they thought that hum was pigeon shit. And so what they would do is they would come up every once in a while and they would take their broom and their cleaning tools and they would shovel out this pigeon shit. And they would go back down and they would still hear the hum. Now they didn't know what it was, but they needed help. So they put out the information. They published their results. They said, everywhere we look, everywhere we point this telescope, it doesn't matter what direction we get this hum, and we don't know why. Someone please help figure out what's going on with our telescope, what's wrong with it. Another group of scientists that was looking for this said, that's not pigeon shit, that's the Big Bang. Okay, what they had accidentally discovered is they accidentally ran into the leftover energy deep in outer space. That was the hum that they were hearing. And the reason that they heard that hum, no matter where they pointed their telescope, is because that energy is the outside of the universe. It's everywhere, okay? It's like trying to point up and not hitting air here on Earth, okay? So what they accidentally found, I think it was pigeon poop, was the leftover energy from the Big Bang. They coined this background radiation, okay? Because no matter where you look, you see this leftover energy, right? So like if we're here, right, and we're looking at the galaxy, we see all the stars, then beyond that, there's an empty space, there's no light. That was the time before, right? Remember, there's 300,000 years before the first starlight. So as we go back in time, as we look deeper, we're looking further back in time, and after that, boom, then they hit that background radiation, right? Now, there have been much better pictures. You can see them online. Just look up the general background radiation of the universe, and you see this beautiful bubble, right, of energy. Now, what's important about that bubble is it's pretty much where we expected to find it. Remember, your friend is 100 miles away. We knew that by doing math. It's a little bit further than 100 miles, but this is about where it needs to be in order to get that 13.8 billion year number Okay? So this was a huge piece of evidence. The cosmic microwave background radiation that we see everywhere, which is just leftover energy from the Big Bang. Now, the second part I'm not going to get into. What was the second thing that I said we would look for? What's the universe constantly doing? Constantly expanding. We're not going to get to that yet, because I still would hopefully like to do our activity at some point. Okay? But what we're going to do is we're going to test this theory. We're going to see how do we know the universe is still expanding. Okay? So, at least I'm going to turn the lights, guys, so watch your eyes. All right. So what I would like you guys to do, I know today was a lot of talking, and we've got about 15 minutes, or less than 15 minutes in class. I'm going to give you exit tickets for the first 2 days, and I would like you guys to work through those and get those back to me today. After today, the exit tickets are mostly going to be online on that Google Classroom. Okay, I provided copies to them so you can see them on the Google Classroom if you want, but they're the same thing. They'll be handed to you right here on paper. I have created these stoplight exit tickets for myself, and they are a very important tool for you and for me. It's not just a main thing that I do at the end of class, but this is a review of the class. So guys, traffic light, what are the colors? Red, yellow, and green, right? The questions in the red section mean something. These are the basic level questions. They're multiple choice, true and false, fill in the blank. They are like, hey, I was here, I had a pulse, I heard you talk about this, I should be able to answer this question. Okay? If not, what does a red light mean? Stop. So if you're struggling with those questions, guess what you need to do? Stop and ask for help. Okay? The middle section, that's yellow. Okay? These are usually going to be, there's going to be some like math, or maybe a couple words, or maybe list something, make a little diagram, I don't know. Okay, but those are the kind of questions in this section. If you're having trouble with those, what does yellow mean?
Slow down.
Slow down, stop if you need to, maybe take a look at your notes, and if you really need to, ask for help. Green, all right, that's a little longer question. Maybe it takes a sentence or two, maybe it takes a little bit more math, maybe it takes a really nice diagram, I don't know. But if you're good with that, what does green mean? You're good to go. Okay? These are worth 10 points. Everything in red is worth 1, everything in yellow is worth 2, green is worth 3, so if you get 7 out of 10, that's a C. These become great study guides. There's one for each class. And if I talk about it in the lesson, we practice it on the practice, and then I put it on here. If you see it 3 places, it's important. Okay? It's a good way to know. I try and get these back to you as soon as I can. Hopefully the next day is not the day after. But you will have these with you before quizzes and tests, so you have things to study from. Okay? Any questions about X tickets? All right. Fill this out. Bring it up to me when you're finished. There is a front and back, just because today we're doing 2 lessons in 1. Okay, normally there's just 1. So go ahead and take a look at those. Use your notes. Add a couple things too. The weight one, remember we wrote down that formula, so go back and find that formula. That's for gravity. Everything else we just talked about. Okay.